A campfire burns at around 1,000 degrees, but inside a jet engine, you are dealing with a continuous 3,500-degree inferno. Welcome back, aviation explorers. If you are new to how aircraft work, you are in the right place. Today, we are looking straight into the engine's hot section. Before we dive into the flames, please take a quick second to like and subscribe so we can keep making aviation easy to understand for everyone. The core of this hot section is the combustion chamber. Its entire job is to take highly compressed air, mix it with a very fine spray of jet fuel, and spark a continuous explosion. You need this massive fire to power the airplane, but that same fire generates enough heat to instantly melt the very metal walls trying to hold it. How do you build a container that can safely hold and control this kind of extreme heat? Older designs used can-type combustors, acting as a circle of separate, isolated cylinders. Engineers adapted this into a can-annular hybrid. The cans remain, but are linked inside a shared outer housing to spread the flame. Modern engines use an annular design, removing the cans completely to create one continuous, undivided ring of fire. Managing the fire while flying is the primary goal, but you also have to think about what happens when you turn the engine off. There is often unburned fuel left behind in that chamber. If it doesn't have a way to drain out, it pools at the bottom. The next time the pilot tries to start the engine, that excess puddle will ignite, creating a temperature spike that could destroy the internal components. Remember, the fire burns at 3,500 degrees, which is far beyond the melting point of the engine's metal housing. To solve this, engineers use the incoming air itself. In this cutaway, air splits into two paths. Primary air flows straight into the center to feed the flames. The remaining secondary air sneaks through tiny slots in the walls, creating a cooler blanket against the metal. By the exit, this fresh air drops the temperature from 3,500 degrees down to a safer 1,500 degrees. The engine uses the exact same air that feeds the fire to build an invisible protective layer around its own walls. Now that the air is safely contained and heated, it rapidly expands, rushing backward out of the combustor and into the turbine section. The turbine works just like a high-tech windmill, absorbing the immense pressure and velocity to forcefully spin its heavy metal blades. As those blades catch the exhaust, they rotate a central shaft that runs all the way back to the front of the engine, providing the mechanical power needed to keep sucking in new air. Even at 1,500 degrees, the heat is harsh on these spinning parts. To survive, the blades are coated in heat-resistant ceramics, acting much like a heavy-duty oven mitt. And looking at this cross-section, you can see the blades are actually hollow. They pipe cooling air up through the core and bleed it out through tiny pores on the surface. The turbine extracts a portion of the exhaust's energy, using it strictly to keep the engine's self-feeding cycle going. Once the turbine has taken the power it needs, the remaining hot gas travels into the very back of the engine, the exhaust section. At this stage, the air is swirling and chaotic. An exhaust cone and a series of metal fins catch the spinning gas and physically straighten it into a solid, unified flow. Looking at the exhaust nozzle flow here, the nozzle slightly squeezes this gas as it leaves. Just like putting your thumb over a garden hose, this increases the exit velocity, which creates the actual thrust. That is the complete loop. Air makes fire, the fire spins the turbines, and the turbines turn the shaft to suck in more air. You've just mastered the hot section of a jet engine. This complex system works because engineers found physical ways to manage extreme heat and massive pressure.